Imagine a trampoline so small it's invisible to the naked eye. Picture a world where the very fabric of reality is manipulated with the precision of a master craftsman. Now imagine this trampoline is designed to bounce not humans, but individual atoms. These atoms, the building blocks of everything around us, are set into motion in ways we've never seen before. Welcome to the fascinating world of atomic trampolines, nanoscopic structures that are revolutionizing how we study and manipulate matter at its most fundamental level. This is where science fiction meets reality, and the possibilities are endless. These aren't your backyard trampolines. They are marvels of modern engineering, designed to operate on a scale so small, it's almost beyond comprehension. Atomic trampolines are meticulously engineered surfaces, typically made of ultra-pure crystals like copper or silicon. These materials are chosen for their unique properties, which allow for the precise control needed in atomic manipulation. The surface is carefully sculpted to have a specific shape and properties, allowing it to trap and manipulate atoms with incredible precision. This level of control opens up new avenues in scientific research and technological innovation. But why go through all this trouble to build a trampoline for atoms? The answer lies in the potential to revolutionize our understanding of the physical world. Because by understanding how individual atoms behave, we can unlock secrets about the universe's building blocks. This knowledge could lead to breakthroughs in everything from materials science to quantum computing. It's like having a tiny laboratory where we can probe the fundamental laws of nature. With atomic trampolines, we are not just observing the universe, we are actively shaping it. Creating an atomic trampoline is a delicate dance between material science and nanotechnology. It demands meticulous precision and a deep understanding of how atoms interact with their surroundings. The first step is selecting the right material for the base of our trampoline. This material needs to be incredibly pure and free from defects, as even the slightest imperfection can disrupt the delicate dance of atoms on its surface. Once we have our pristine base material, typically a silicon wafer, we need to create the trampoline surface. This involves depositing a thin layer of another material, often a metal like gold or copper, onto the base. Before we can even think about depositing our trampoline material, we need to ensure our base is impeccably clean. We're not talking about a quick wipe with a cloth. We're talking about removing every single atom or molecule that doesn't belong. This cleaning process happens in a highly controlled environment called a clean room. Here, the air is constantly filtered to remove dust particles, and workers wear special suits to prevent contamination from skin cells or hair. Why such extreme measures? Because even a single speck of dust can be gigantic compared to the atoms we're working with. Any contamination can disrupt the delicate balance of forces on the atomic scale, rendering our trampoline useless. With a spotlessly clean base, we can now focus on creating the foundation of our atomic trampoline, the crystal structure. This structure dictates how atoms will interact with the surface, ultimately determining the trampoline's effectiveness. Using techniques like molecular beam epitaxy, we deposit atoms of our chosen material onto the base one by one. These atoms self-assemble into a specific crystal structure, guided by the underlying base material and carefully controlled growth conditions. This process is akin to building a Lego tower atom by atom. Each atom needs to be placed precisely to create the desired structure. The resulting crystal surface acts as the platform on which our atomic trampoline will be built. Section 5. Atomic Lego, depositing the trampoline material. With our crystal base ready, it's time to add the final crucial element, the trampoline material itself. This material, often a different element from the base, is carefully chosen for its specific interaction with the type of atom we want to bounce. Again, we employ techniques like molecular beam epitaxy or sputtering to deposit a thin film of the trampoline material onto the crystal base. This film needs to be incredibly thin, often just a few atoms thick, to ensure the underlying crystal structure influences the atoms we want to study. This process requires incredible precision. It's like draping a silk sheet over a rose without crushing a single petal. The result is a meticulously engineered surface capable of trapping and manipulating individual atoms. Section 6. Testing the bounce, characterizing the atomic trampoline. Our atomic trampoline is built, but how do we know if it works? This is a crucial question that drives our next steps in the lab. How can we be sure it's capable of bouncing atoms in the way we need? To answer this, we need to delve into a series of precise and detailed tests. The answer lies in a suite of sophisticated characterization techniques. These techniques allow us to probe the atomic scale properties of our trampoline. One such technique is scanning tunneling microscopy, or STM. This powerful tool is essential for our analysis. This tool uses a sharp, atomically precise tip to scan the surface of our trampoline, mapping its topography with incredible detail. The precision of STM allows us to see features as small as individual atoms. By analyzing the STM images, we can see if the trampoline has the desired structure, and if there are any defects. This helps us ensure the trampoline's surface is perfect for our experiments. Another technique is atomic force microscopy, or AFM. This method complements STM by providing additional insights. This method uses a tiny cantilever with a sharp tip to feel the forces between the tip and the trampoline surface. The AFM can measure forces with incredible sensitivity. By analyzing these forces, we can learn about the trampoline's stiffness, its ability to trap atoms, and how atoms behave on its surface. This comprehensive analysis ensures our atomic trampoline is ready for the next phase of experimentation. Section 7. Safety first. Handling with atomic precision. Working with atomic trampolines is not without its challenges. These nanoscale structures are incredibly delicate and require meticulous care in handling and operation. One of the biggest concerns is contamination. As we discussed earlier, even a single stray atom can disrupt the delicate balance of forces on the atomic scale, rendering our trampoline useless. Therefore, we must maintain the same level of cleanliness and precision throughout the trampoline's lifespan. Furthermore, the techniques used to characterize and manipulate atoms on the trampoline, such as STM and AFM, require specialized equipment and expertise. Operating these instruments demands a steady hand, patience, and a deep understanding of the underlying physics. Section 8. Beyond the bounce applications and future implications. Atomic trampolines, despite their seemingly esoteric nature, hold immense promise for a variety of fields. These tiny structures, which can manipulate individual atoms with precision, are not just a scientific curiosity, but a gateway to groundbreaking advancements. By allowing us to control and study individual atoms, these nanoscale structures are pushing the boundaries of our understanding in physics, chemistry, and materials science. The ability to observe and manipulate atoms at such a detailed level is akin to having a new lens through which we can explore the fundamental building blocks of matter. One exciting application is in quantum computing. Quantum computers, which leverage the principles of quantum mechanics, promise to solve complex problems that are currently intractable for classical computers. Atomic trampolines can be used to trap individual atoms, which can then be used as qubits, the building blocks of quantum computers. These qubits can exist in multiple states simultaneously, enabling quantum computers to perform many calculations at once. By manipulating the state of these trapped atoms, we can perform computations that are impossible for classical computers. This could revolutionize fields such as cryptography, material science, and complex system simulations. Beyond quantum computing, atomic trampolines are enabling advancements in fields like nanoscale sensing, catalysis, and even drug delivery. Nanoscale sensors can detect minute changes in the environment, leading to more sensitive diagnostic tools and environmental monitoring systems. By precisely controlling the interaction of atoms with their surroundings, we are opening doors to new materials with tailored properties and devices with unprecedented capabilities. These materials could lead to stronger, lighter, and more efficient products in various industries. As we delve deeper into the world of atomic trampolines, we are only beginning to scratch the surface of their potential. The innovations that arise from this research could transform our approach to technology and science. These nanoscale structures, born from the marriage of meticulous engineering and fundamental physics, are poised to revolutionize our world in ways we can only begin to imagine. The future implications of atomic trampolines are vast, and their applications could touch every aspect of our lives, from healthcare to computing and beyond.